In this class, we will discuss how we can derive the shape function for a two-noded beam element. So that is also called as Hermitian shape functions. So in the case of beam element, bending effect will be there, and you know from the elements of strength of materials, there is a relationship between the rotation and the deflection. So you have, suppose if this is a beam. So when loads are applied on the beam, it deflects like this, and this is the rotation of the slope, and this is the deflection y. So there is a relationship between these two. Theta, which is very much equal to tan theta, because theta is very small, which is given by dy by dx from the differential calculus. That equation holds good here. So by knowing the deflection, we can always find out the rotation also by using this relation. Now in the case of a beam element, what happens? I have considered a two-noded beam element. 1 and 2 are the nodes here. I will take 2 degrees of freedom at each node. One is the vertical translation and Q1, and another one is the rotation Q2. And here Q3 at the other node, Q3 is the vertical translation, Q4 is the rotation at node 2. So I have taken upward displacement, vertical displacement as positive, that is Q1, Q3, they are positive in the upward direction, and Q2 and Q4 I have taken the rotation anti-clockwise as positive. Now the shape functions I will call them as, since they are also called as Hermitian shape functions, I will take them as h1, h2, h3, h4. These shape functions corresponds to these 4 nodal displacements. Here Q1, Q2, Q3, Q4, they are called as the nodal displacements. So these shape functions correspond to these nodal displacements. Now we have to find out one by one all the 4 Hermitian shape functions. So one for each nodal displacement by assuming the shape function in this form. So I am going to use a natural coordinate system. So it is a one-dimensional element. Beam is a one-dimensional element here. So only zeta will be there as the natural coordinate. So what I will do here is, you know that the maximum value and minimum value of the natural coordinates are 1 and -1. I have taken, I will take the zeta value as -1 at this node and +1 at this node. Naturally, at the center of the element, that value of zeta becomes 0. So here, at node 1, zeta is -1. At node 2, zeta is +1. So they are the boundary conditions. Now I will assume the shape function in this form: a plus b zeta plus c zeta square plus d zeta cube. So third order I am going to take, because you have 4 boundary conditions here. So using those 4 boundary conditions, you can solve for these 4 unknowns a, b, c, d. Let us take the first, we will find the Hermitian shape function h1, which corresponds to the nodal displacement q1. So q1 is the vertical translation at node 1. So the boundary conditions are like this. So let us assume this is as a polynomial like this. Now I am going to use 4 boundary conditions to find out the 4 unknowns a, b, c, d. Once you find out these 4 unknowns a, b, c, d, you can write the shape function h1. So h1 is a function of zeta. So all these shape functions, they are all functions of natural coordinate zeta. Only one coordinate I am going to take because it is a one-dimensional element. Now at node 1, now the boundary conditions run like this. There are 4 boundary conditions. At node 1, h1 is equal to 1, zeta is equal to -1. So because at node 1, what happens here, this h1 corresponds to q1. Please note that h1 corresponds to q1, h2 corresponds to q2, h3 corresponds to q3, h4 corresponds to q4. Now at node 1, what happens at this node, h1 value is 1. Now I am going to take the first nodal displacement, that is q1, and all the others I am going to make it as 0. So So what happens here, h1 is equal to 1 here because the maximum value of h1 is 1, and in the direction of q1 the value of h1 is 1 and zeta value is minus 1 at the node 1. Now substitute for h1 and zeta in this general expression which we have observed for h1, and if you simplify you get the equation h1 is 1 is equal to a, zeta is minus 1, so minus b plus c minus b. So that is called as equation 1. So using the first boundary condition we have got this equation. So since there are 4 unknowns, we need to use 4 boundary conditions. So the second boundary condition is at the same node 1, so you have the derivative 0 because since there is a relationship between slope and deflection here, since h1 is constant, h1 is 1 here, its derivative with respect to zeta becomes 0. Now what I will do here is I will differentiate this with respect to zeta. If you differentiate this with respect to zeta, dh1 by d zeta will be b plus 2c zeta plus 3d zeta square. So that's what I am going to get here. Since I know this is 0, LHS becomes 0 here, and zeta you have to put minus 1, so you will get another equation. So at node 2 you have got 2 equations now. Now at node 1 you got 2 equations. Now we will move to node 2. The difference is at node 2 the value of h1 becomes 0. This is because h1 corresponds to q1, so I have to take the other displacements as 0, so this becomes 0, but only thing is zeta becomes 1 here. So substitute these two values in this, you get another equation, a plus b plus c plus d is equal to 1. And at node 2 once again derivative also is 0, so if you substitute the derivative of this and put zeta as 1, you are going to get one more equation, so b plus 2c plus 3d is equal to 0. So that is the fourth equation. So by applying the boundary conditions, 2 equations we get at node 1, 2 equations we get at node 2. Now totally there are 4 equations. Solving all these 4 equations, we can evaluate the a, b, c, d values. So in this case, you are going to get these things. So by elimination, Gaussian elimination method, you can proceed. So these are the values we got. So finally, after getting the values of a, b, c, d, substitute the values, you will get h1 as 1 by 4 into 2 minus 3 zeta plus zeta cube. So that's what we get for the first Hermitian shape function. Now to find the second, so all the 4 we have to find out. To find the second Hermitian shape function which corresponds to q2. Please note it is for q2. So for same procedure is adopted, we will assume h2 also in the same manner as a polynomial in zeta, third degree polynomial. So and let us start applying the boundary conditions. So here in this case the difference is at node 1 h2 becomes 0. At node 1 h2 becomes 0 and zeta is equal to minus 1. Zeta is equal to minus 1. Because this is because, see here, now I am writing for h2. h2 corresponds to this q2. Therefore, q1 I have to make it as 0. So, except q2, the other displacements, nodal displacements corresponding shape function for that nodal displacement, we have to make it as 0. So in the second, when we are finding h2, so please note that the second will be equal to 1. That is dh2 by d zeta is equal to 1. That corresponds to this. Whereas because this is the slope, it refers to the rotation aspect. So only this will be 1. All the others are 0. You can see here. So all these are 0. This is how you have to remember. So this becomes 0, and of course zeta value at node 1 it will be minus 1, at node 2 it will be plus 1. So once you use these conditions, you will get one more set of 4 equations in a, b, c, d. So if you solve them, you are going to get a, b, c, d values, and if you substitute them once again, you are going to get h2 as 1 by 4 into 1 minus zeta square plus zeta cube. That is the second Hermitian shape function. Now coming to the third Hermitian shape function, when you are speaking of third one, once again h3 is assumed like this, but h3 corresponds to q3. Please note. So the others are zeros. Q1, Q2, Q4, those things we have to make it as 0. That means, so here first one is 0, second one is 0, third one is 1 and fourth one is 0. Please note that. So like this, so when you move from H1, so in the case of H1, see, first one is 1, second one is 0, third one is 0, fourth one is 0. So only first one is 1. Whereas in second case, second one is 1. Others are zeros. Okay? In the third one, first and second will be 0, third will be 1 and fourth will be 0. So like this. So we have to take the Hermitian function, either it will be 0 or 1, and the derivative either it will be 0 or 1, depending on which nodal displacement you are considering. So once again here, after substituting the values of zeta, you are going to get another set of 4 equations. If you solve them by Gaussian elimination method, you will get the values of ABCD, substitute back. So in that H3, you will get 1 by 4 into 2 plus 3 zeta minus zeta cube as the shape function H3. Now shape function H4 corresponds to this Q4. So when you are finding Q4, H4, so the other three you have to take it as 0, corresponds to Q1, Q2, Q3, you have to take it as 0. Please note here, I have written here H4 is equal to 0, dH4 by d zeta is equal to 0 at node 1, whereas at node 2, H4 is 0, but dH4 by d zeta is equal to 1. See the order here, so when you remember the order, you can easily differentiate and substitute the values, and you can solve the set of equations. So once again you are going to get one more set of equations by applying these 4 conditions. A, B, C, D you are going to get, and finally substitute those values, you will get the Hermitian function H4. That means finally what we can write here is, in the case of a beam element with 2 degrees of freedom and 2 nodes. So totally you will be having 4 shape functions. So they are denoted by H1, H2, H3, H4. So I can write like this. So the shape functions H1, H2, H3, H4, Hermitian shape functions for a beam element can be written as 1 by 4 is common here. You can see 1 by 4 is common in all the terms. H1 is 2 minus 3 zeta plus zeta cube. So 2 minus 3 zeta plus zeta cube. The second term H2, 1 by 4 into 1 minus zeta square. So 1 minus zeta square plus zeta cube. That's what you get for H2. Then H3 is 1 by 4 into 2 plus 3 zeta minus zeta cube. And the last one H4 will be 1 by 4 into minus 1 plus minus zeta, minus 1 minus zeta plus zeta square plus zeta cube. So this is how we can write the shape functions of a two node beam element. So which gives the expression in terms of the natural coordinates. Just by substituting the value of zeta, you can find out the values of the shape functions, corresponding values of the shape functions. For example, if I want the shape function Hermitian shape function at zeta is equal to 0. Zeta is equal to 0 means it is at the midpoint of the beam or center of the beam. So if you put zeta is equal to 0, you are going to get the Hermitian shape function at the center midpoint. Now what you can write here is, so just I can show in the form of a table column. So zeta is equal to minus 1, zeta is equal to 0, zeta is equal to plus 1. So these are the values of zeta at the node, first node this is the value, at the second node this is the value, and at the center this is the value, center point of the beam, this is the value of zeta. Now you can always get the values of H1, H2, H3, H4 at those 3 points. So at whatever point you require, just by putting the values of zeta, you can get the values of the Hermitian shape functions. So suppose if you put for h1, the plotting is like this. So if you have to take zeta is equal to minus 1 means, so 2 plus 3 minus 1, okay, 2 plus 3 minus 1 into 1 by 4 is there of course. So it becomes here 5 minus 1 4, 4 divided by 4 1. So you are going to get the value as 1. When you put zeta is equal to 0, it becomes 1 by 4 into 2 which is half, so 0.5. The value of h1 at the center of the beam is 0.5. Then when you take plus 1, it is 1 by 4 into 2 minus 3 plus 1 which is 1 by 4 into 0, so this becomes 0. Please note that the value of h1 at the other node it is 0. At the other node means at the node 2 it is 0. That means it is actually it is having third degree. Third degree means, so you can always plot. You can always plot. So this is zeta is equal to 1, zeta is equal to 0, zeta is equal to minus 1, node number 1, node number 2. If you want to plot the h1 Hermitian shape function h1, so here it is 1. The value of h1 here is 1. h1 is equal to 1 here, whereas at zeta is equal to 0 it is 0.5. Here it is 0.5, whereas it is 0 here. So if you want, you can have a value zeta is equal to 0.5 also, and you can find out at that point also. Then you have to join the points by a cubic parabola. So something like that you have to join. So you are going to get a curve something like this, because it is of third order. So this is the variation of h1 over the length of the beam. So it is completely positive. So this is how you can always get the value here. You can always get the value here if you want any value. For example, if you take here, it is zeta is equal to 0.5, zeta is equal to minus 0.5. So just substitute those values in this and simplify. You will get the corresponding values of zeta. So similarly, if you want to plot h2, Hermitian shape function h2, I have to use the second expression. So put zeta is equal to minus 1 here. So it becomes 1 by 4, 1 plus 1, minus 1, minus 1. So like this. So that means it becomes 0. So please note that the value of h2 is 0 at node 1. And when zeta is 0, it is 1 by 4. You can see it is 1 by 4. That is 0.25. Then when zeta is plus 1, it is 1 by 4 into 1 minus 1 minus 1 plus 1. 1 minus 1, then minus 1 plus 1. That means this also becomes the value of h2 is 0. The value of h2 is 0 at the second node. So that means it will take a shape something like this. So if you plot h2, so it will take a shape like this. So it is 0.25 at the center, 0 here, 0 here, something like this. So this value is h2. So this value is 0.25. Of course, I am not plotting to scale here. So this is 0.5, this is 0.25. So just anyway, it is a cubic parabola, something like that. So h3 similarly you can get by substituting values here and simplifying. h4 also you can get, and later on you can plot. So that means in general, what you can say here is all these shape functions, they give an idea how the displacement or the rotation takes place over at different points along the length of a beam. By knowing the nodal displacements q1, q2, q3, q4, and by knowing the shape functions, you can always obtain the displacements and the rotations at any point along the element or on the element.